Last time, in the sorting video, we caught something strange. Merge sort and quicksort both solved a big problem by calling themselves on smaller pieces. That trick has a name. Recursion, a function that calls itself. It looks like magic. Watch. Here is factorial of 4. To solve it, it calls factorial of 3. Which calls factorial of 2. Which calls factorial of 1. Which calls factorial of 0. The calls pile up into a stack. Then, one by one, they hand their answers back up. 1, 1, 2, 6, and finally 24. It looks like magic. But it is just a stack. Let me show you exactly how, visually. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and Data Structures, Visually Explained. 23 of them, each with a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us take recursion apart. Every recursion, every single one, needs exactly two things. Miss either one, and it breaks. Rule 1. A base case. That is the stopping point. A version of the problem so small the function can answer it instantly, with no more calls. For factorial, the base case is simple. Factorial of 0 is 1. Done. Rule 2. A recursive case. This is the part that calls itself, but on a smaller input, one step closer to the base case. Factorial of n calls factorial of n minus 1. Every call shrinks the problem. Here is why both matter. The recursive case moves you toward the base case. The base case catches you and stops the fall. Now take away the base case. Nothing stops the calls. The function calls itself, which calls itself, forever. Each call eats a little memory on the stack. The stack fills up, and your program crashes. That crash has a name you will meet a lot. Stack overflow. So the rule is simple. A base case that stops it, and a recursive case that moves toward it. Both. Always. Now the part that makes it click. The call stack, drawn live. This is the whole idea. We are going to compute factorial of 4. Think of the stack as a pile of sticky notes. Every time a function calls another, we drop a new note on top. That note is a stack frame. It holds the paused call, waiting for its answer. We start. Factorial of 4 wants 4 times factorial of 3. But it does not know factorial of 3 yet. So it pauses, and calls it. Push a frame. Factorial of 3 needs factorial of 2. Pause, push. Factorial of 2 needs factorial of 1. Pause, push. Factorial of 1 needs factorial of 0. Pause, push. Now factorial of 0. This is the base case. It calls nothing, it just returns 1. This is where the pile stops growing. Forget this line, and we push frames forever. That is the stack overflow from a minute ago. Now watch the pile unwind. This is the beautiful part. The answers flow back up. Factorial of 0 returned 1. Pop that frame. Hand the 1 up. Factorial of 1 was waiting to compute 1 times that answer. 1 times 1 is 1. Return 1. Pop. Factorial of 2 computes 2 times 1. That is 2. Return 2. Pop. Factorial of 3 computes 3 times 2. That is 6. Return 6. Pop. And factorial of 4, the very first call, finally gets its answer. 4 times 6. 24. Pop the last frame. There it is. The calls piled up on the way down to the base case. The answers flowed back up on the way out. 1, 1, 2, 6, 24. That pile, growing, then unwinding, is the call stack. That is recursion. No magic. Just a stack. So where does this actually show up? Everywhere the good stuff lives. First, divide and conquer. You saw this in the sorting video. Merge sort and quicksort split the list in half, call themselves on each half, then combine. That splitting and self-calling is recursion. It is the engine under the fastest sorts. Second, trees and graphs. A folder holds files, and other folders. To walk the whole tree, you handle one folder, then call the same function on each folder inside. File explorers, web pages, game scene graphs, all trees, all walked with recursion. Third, nested data. Think JSON, objects inside arrays inside objects. A function that calls itself on each nested piece is the natural fit. And fourth, the classic warm-up problems. Factorial. Fibonacci. Summing a list by adding the first item to the sum of the rest. Once you see the pattern, you cannot unsee it. Solve a big thing by solving a smaller version of the same thing. But recursion has a sharp edge. Let me show you how it goes wrong. This ties straight back to Big O. Meet naive Fibonacci. Each Fibonacci number is the sum of the two before it. So fib of n calls fib of n minus 1, plus fib of n minus 2. 2 calls each time. Elegant, and, done this way, a disaster. Watch the call tree for fib of 5. It calls fib of 4 and fib of 3. Fib of 4 calls fib of 3 and fib of 2. But look, fib of 3 is now computed twice. Go deeper and it gets worse. Fib of 2 shows up 3 separate times. The same little subproblems get recomputed again and again, in branches that never talk to each other. The tree does not grow. It explodes. Every level roughly doubles the number of calls. That is O of 2 to the n, exponential. Fib of 5 is 15 calls. Fib of 50. More calls than there are seconds in your life. The same clean idea now hangs your machine. Here is the good news, and we go deep on it another day. There is a fix. You remember answers you already computed instead of redoing them. It is called memoization, and it collapses that exploding tree into a straight line. Recursion is not the villain. Recomputing the same thing is. Here is the whole thing in real, runnable Python. Factorial, in 4 lines. We define factorial of n. First, the base case. If n equals 0, return 1. That is the stopping point. Otherwise, the recursive case. Return n times factorial of n minus 1. That is the call to itself, on a smaller number. That is it. Base case on top, recursive case below. Read it out loud, and it is almost the English definition. Factorial of n is n times the factorial of 1 less, unless n is 0, in which case it is 1. Every recursion you write has this same shape. A base case that stops, and a recursive call that shrinks the problem. Let us lock it in. Recursion is a function that calls itself. It needs 2 things, always. A base case that stops it. And a recursive case that moves toward that base case, one smaller step at a time. Under the hood, it is a stack. Calls pile up as you go deeper, down to the base case. Then the answers unwind back up. Factorial of 4, 1, 1, 2, 6, 24. Forget the base case, and the stack fills forever. Stack overflow. And beware the naive Fibonacci trap. Recomputing the same values turns a clean recursion into an exponential mess. That is recursion. Not magic. Just a stack that fills up, and empties out. So that is recursion. A function that calls itself. A stack that piles up, then unwinds. The idea humming under merge sort, quicksort, and every tree you will ever walk. Next in this series, we switch from algorithms to the data structures underneath them. And we start with the one that feels impossible. Hash tables. How does a dictionary or a set find any key in O of 1? Instant lookups, no matter how much data you throw at it. How does that even work? That is your next watch. And if you want the whole picture, 23 algorithms and data structures, each with a diagram and clean Python. My book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.